This video presents our work, Task-Decoupled Bézier Surface Constraint for Uneven Low-Light Image Enhancement. The goal of low-light image enhancement is to increase the brightness of originally dark images through algorithms, thereby enabling the utilization of more useful information within the image. Although existing deep learning-based methods can achieve overall brightness enhancement, they often cause overexposure in images with uneven illumination or complex color distributions, leading to the loss of original useful information. The overexposure problem in the enhancement process arises because most networks adjust only the global brightness distribution, neglecting the fact that illumination in an image is not perfectly uniform. To enable independent and precise control over brightness, we decouple the LLIE task into two subtasks, shading and brightening. Herefore, we can employ a method to address this issue. Converting the image to HSB channel format makes the brightness information and color information of the image separate. In the HSB color representation, H, S, and B denote the hue, saturation, and brightness of an image, respectively. We designed a branch diffusion model with one encoder and two decoders. This model separately performs brightness, B, and color, HS, enhancement and reconstruction through the two decoders, thus avoiding interference between the two tasks. However, simply decoupling the task does not completely solve the problem of uneven brightness distribution of the reconstructed structure. For this reason, we need to constrain the brightness of the reconstructed image. To implement such a constraint, we need to find a mathematical computation that can express the smoothness of the image, and eventually, we adopt a Bézier surface as a loss constraint on the brightness smoothness of the image. A Bézier surface is a smooth parametric surface defined by a set of control points and basis functions, commonly used in computer graphics to model complex surfaces. It possesses the following characteristics. It is defined by a finite set of discrete control points, exhibits smooth global continuity, allows local modifications without causing drastic global changes, and demonstrates excellent smoothness. Through computation, we take the brightness values of the highlight map as control points to construct a Bézier surface. The brightness Bézier surface is then utilized to further constrain and restore the unevenly illuminated regions. In the training process, we not only need to use GT as a target constraint, but also need to use the GT smooth brightness distribution as a constraint, so as to make the brightness distribution of the reconstructed image more uniform, thus avoiding the problem that the network is difficult to deal with the unevenly illuminated regions in the inference process. Controlling the image's brightness distribution through the Bézier surface allows for better low-light enhancement, but this method is not without its flaws. To some extent, the Bézier surface may lose certain details in the reconstructed image, such as high-frequency details that are rich in texture. Therefore, to avoid such a problem, we employed a Fourier transform-based space-frequency reconstruction module, which allows the network to better focus on the detailed information that the Bézier surface fails to control, by reconstructing the image in Fourier space with a trivial increase in parameters. We conducted quantitative comparisons between our method and multiple SOTA models using several widely adopted datasets. The table presents the PSNR and SSIM results of different methods across these datasets. We further analyzed the brightness variations in the enhanced images produced by different methods. As shown in the figure, we selected a row of pixels from the enhanced image, calculated the values in the brightness channel, and visualized them in a line chart. The red and blue curves represent the brightness variations of the ground truth image and the enhanced images generated by various methods, respectively. This figure shows a comparison of our method trained on the LOLV1 dataset and tested on an unsupervised dataset. As can be seen from the images, our method achieves superior restoration performance compared to other approaches. As shown in table, we conducted an exploration on the LOLV1 dataset from three aspects: network branches, Bézier surfaces, and the spatial frequency reconstruction module. Using the network branch structure alone, the model performance improved by 0.3 dB compared to the baseline. However, when using the Bézier surface independently, the model's performance unexpectedly declined in terms of both PSNR and SSIM metrics. This does not imply that the Bézier surface is ineffective, as the inclusion of the Bézier surface resulted in a performance difference of 0.69 dB depending on whether the network branches were used. It is important to note that, although PSNR experiences some loss when the SFRM is used, the SSIM metric, which represents image details, shows an improvement, which is consistent with the theoretical explanation presented earlier. We tried different loss weights lambda and Bézier surface control points step n on the LOLV1 dataset, and the optimal parameterization scheme was selected through SSIM metrics. Thank you for watching.